All right, so welcome everyone to the webinar today offered by the American Rock Mechanics Association and its tunneling committee. My name is Reza Hedayat. I have the pleasure of hosting the webinar today. We are monitoring attendance. For whatever reason, we have the waiting room option implemented today. So Jamal and I, as the co-chairs, will be doing our best to admit as soon as we have the folks joining here. Today's webinar, in terms of the structure, will be 1 hour in duration. Will consist of 40-minute presentation and 20 minutes of question and answer. Please feel free to post your questions at any given time using the Q&A option that you see at the bottom panel of your Zoom. Of course, we will have time at the second portion of the webinar to have also the option to hear from you about questions that you would have. So we ask for everyone to please mute your microphone so you can be on the listen-only mode, but we would love to hear from you during the Q&A period. For live attendees who are joining us, if you're interested in receiving a professional development hour certificate for this webinar, please contact learn@mines.edu so you can receive the online certificate at the minimal cost of $10. So it's my distinct pleasure to introduce our speaker today, Carlos Jaramillo, who has received his bachelor's degree in civil engineering from Universidad Nacional de Colombia and master's of science degree in civil engineering from University of Minnesota. Carlos has over 40 years of experience and has been involved in all design and construction aspects of many infrastructures, including a major hydropower, water resources, and other infrastructure projects, and has led design teams or directly performed design studies for tunnels, caverns, shafts, and other underground structures. Carlos has collaborated with designers and contractors on tunnel boring machine selection, technical specification, and contract document development, and provided construction phase support. Carlos has been appointed to numerous panels of experts and a board of consultants for hydropower projects in North and South America, as well as South and Southeast Asia. Carlos is also a contributor to major technical journals as an author and technical reviewer. Carlos, a pleasure to have you. Please feel free to proceed with your presentation.
Thank you, Reza. Well, my idea is to talk about tunnels in rock and the effect of earthquakes have on them. This is a subject that well, let's skip this. It's a subject that has been starting relatively recently. For a long time, tunnels and underground structures were considered to be inherently safe during earthquakes. But even from last century, at the beginning, during the aftermath of the San Francisco earthquake, they noticed that not all tunnels were safe during the earthquake. There are two specific cases, the Rice Tunnel and the San Andres Reservoir outlet, that were directly impacted by the fault, the movement of the San Andres fault, and they were displaced. In this case, I'm showing the photograph of the outlet for the San Andres Reservoir that was displaced about 2.5 meters. It was relatively concentrated, and it was a masonry line tunnel, and as you can see, it suffered quite a bit. It didn't collapse, and the tunnel is still used as part of the reservoir, and you can see the kink is still there. It was never realigned, so the outlet still has a kink in the plan view. After that, somehow it's not moving. Oh, there. After that, in the mid-70s, there were several studies compiling what had happened in different earthquakes. one was based on Rosen's Master of Science thesis. He did he compiled a lot of case histories, and they were later published with his advisor Dowding in 1978, and that's the paper that is better known. But in his thesis, Rosen not only compiled the cases, but he also discussed how an earthquake could impact the tunnel and identify the particular cases, how things have gone in those events. A lot of the data was from Japan, where they had quite a bit of underground infrastructure. Then in 1999, during the Chechen earthquake in Taiwan, there were impacts in many tunnels, and they collected good data. Later, other events in Japan, the Niigata event or Chuetsu, and most recently the 2008 Wenchuan earthquake in China that allowed collection of data of behavior of tunnels in many different locations. There was a very important paper sponsored by the International Tunnel Association and led by Hashash from University of Illinois that has become the most important reference on the subject of how to design the tunnels for earthquakes. This paper and many after that deal mostly with design of the secondary line, the final line. How do the earthquakes impact tunnels in rock in particular? Well, the weakest part of the tunnel during an earthquake seems to be the portals. Many of the case histories show how either the portal structure is a fracture or collapse, or the landslides that occur near the portal, and how is the access to the tunnel is affected. But inside the tunnel, there are also many impacts, mostly fractures in the tunnel due to the movement of the seismic wave through it, and how it changes the stresses within that lining. And we have to look, well, what is important, what we have to look for. Definitely the magnitude of the event and how close the event is to the tunnel. Then the direction of the waves respect to the tunnel. Some are longitudinal and go along the tunnel, and then it creates areas of compression and extension. If it comes in a different direction, then the lining is compressed or oval, and all those have different effect on the lining itself. Also very important is the rock mass quality. It can also happen, and is relatively frequent now, is the tunnels cross faults that are either active or that during the seismic event, have movement, even if they were not the causative fault. These cases are becoming very important recently. When in California, the high-speed rail that is being constructed, two of the most important sections that connect directly to LA or to San Francisco have to cross very active faults. And one case that is already constructed is the Bay Area Rapid Transit System. The tunnel that crosses the Berkeley Hills crosses the Hayward Fault. In this area, the Hayward Fault is creeping constantly, and they have to go inside and keep re-excavating the section to maintain the clearance for the BART trucks, cars to move through. There is a plan of actually going in and reinforcing this area because it's expected that in the next 25 years there will be a larger movement in this fault, and it will completely stop the movement of the cars through this tunnel. When we look at the seismic design of tunnels, we look at how we usually go and design tunnels. Well, we use empirical methods, QRMR, analytical using convergence confinement, numerical methods using either finite difference of finite elements to decide what ground support we require at the time. Then we go and design a final lining. It could be either shotcrete, concrete, reinforced concrete, or plain concrete in many cases, precast concrete segments if we are using a TBM. And in many of those cases, these methods don't account for seismic activity. The classical methods, the QRMR and convergence confinement and the sequential excavation method or an ATM, they don't account directly for the impact of earthquakes. So the primary support of the tunnels is only based on gravitational laws. They do include block size, joint characteristics, groundwater and in situ stresses, but the main goal is to support the ground, the excavation, as cheaply as possible, and then move from there and construct the concrete lining. Now, the concrete lining, since the construction of the BART in the late 60s, when they started with that, they created or set a specific seismic design criteria. And here in California, since the 2000s, 2010 or so, the city of San Francisco started reevaluating many of the tunnels that were used to bring water supply to the city, and developed a series of seismic design criteria, and they were used for the New Irvington Tunnel, for example, and they were also used to for several of the pipelines that had to be re-evaluated and some reconstructed, and these criteria were also used for the Bay Tunnel that carries one of the pipes under the bay from the Fremont side or to the peninsula side in San Francisco. most of the cases we are looking at the performance-based design, but in some cases we get into some conditions of concrete design that are not quite covered with the usual ACI codes, and we start using the man capacity radius that are beyond 1 up to 2. So we are expecting big damage into those concrete sections. And we start looking into specific details, like the photo I showed there, that is a detail that is included in the Bosphorus tunnel in Turkey, that where very large earthquakes are expected and happen very frequently. And they provide these joints to accommodate some of the movement expected during the earthquakes. We look at some case histories that are relatively well documented. The Sanji Railway Tunnel in Taiwan, the Bolu Road Tunnel in Turkey, and Longxi Road Tunnel in China. The Sanji Railway Tunnel, it carries one of the high-speed rails connecting the cities in Taiwan, and it was very close to the rupture of the Chichen earthquake. If you could see my cursor, the location of the tunnel is more or less there, and the line in red is the rupture of the Chichen earthquake. So it was very close to it, and it suffered. It was excavated using sequential excavation methods. It had a primary support of shotcrete and rock bolts, not shown in the figure, and it had an internal lining in some parts of plain concrete. But it was expected to support the loads, and according to the criteria that were used, was enough for that. The tunnel is around 6 meter internal diameter and is in sandstones and shales. After the event, they visited it and they found quite a bit of damage. And the damage occurred all along the tunnel from moderately to highly fractured rock areas. So there was not a particular connection to the type of ground. It was more concentrated in areas where they had refuge chambers. So the geometry changed from the traditional tunnel section, and it had an opening, and some areas collapsed. But if they had used reinforcement in the lining, they could have avoided a lot of this damage. The Bolu Road Tunnel, that tunnel had many problems, even during construction, not related to the earthquake itself. It was exposed to 2 earthquakes: the Kocaeli earthquake that was 100 kilometers away, and then the Duche earthquake that was close by, and created very large stresses on the cross section, collapsing some of it. Again, the tunnel was constructed by sequential excavation methods. It had a unreinforced concrete lining, and beyond the earthquake, the ground was a very difficult ground. It was under high stresses. Some of the areas squeezed, and it will be a great case history just to study how to excavate a tunnel under these very difficult conditions. But it also suffered during the earthquake, and areas that had already been stabilized collapsed. Unfortunately, the photo I can show is not very good, but it also showed that one of the exploratory tunnels that were being constructed ahead of the main tunnel, and you had a circular cross section that also had a big impact, and the concrete lining was fractured and collapsed in some areas. Again, when they repaired this tunnel, they included a series of joints that allow different sections of the tunnel to displace and take some of the stress out of the lining, and improve the survivability of the tunnel in case an earthquake similar to this repeats itself. And that's very common because the Northern Anatolia fault is very active, and most of the segments of the fault rupture in about 50 to 100 years interval. Then we can look at the Longshe Road Tunnel. Again, this one was very close to the fault, and I have conflicting information in this one. As you can see in this figure, it says that the epicenter was 18 kilometers away. However, I have information from a different paper that says only 2 kilometers away. So in any case, it was very close, and it suffered quite a bit during the earthquake. It was a big tunnel again. It was constructed by sequential excavation methods. It did have reinforced concrete, but the reinforced concrete lining failed in many locations and collapsed in some areas. You can see the photograph, all the fractures and in the one in the bottom part of the concrete lining collapse. In that one in particular, you don't see reinforcements. So it might be that some areas were not reinforced. So when they repair this one, they reconstruct the lining with additional reinforcing, and is operating normally. But again, the ground motions that occurred in this earthquake were very high, and this is only one of the examples that of tunnels that fail. There is a concrete face rockfill dam located very close to the fault trace, and suffered quite a bit during the earthquake, but it survived the earthquake. But one of the tunnels that are used for outlets collapsed and had to be repaired. Besides the ground motions generated by the earthquake, when the tunnel crosses the fault, and the fault is active or can suffer a sympathetic movement due to the earthquake in the main fault, there is additional stresses that have to be considered in the design of the tunnel. As I showed earlier, the San Andreas Reservoir outlet crossed the San Andreas fault and was displaced by it. The Bolu tunnel can be displaced by sympathetic movement in some faults that are not the main fault. One interesting case is the Claremont tunnel here in San Francisco, that carries water to the East Bay, to Oakland and other cities in the East Bay. That will be water for around 1 million people. And it crosses the Hayward Fault. So they did a lot of work to mitigate the potential impact of an event on the Hayward Fault. And in case this particular section of the fault displaces, the water supply will still be safe and can be reestablished within hours. We already mentioned the BART tunnel going through the Berkeley Hills. Right now is under construction a project in LA that carry effluent of the treatment plant to an outfall tunnel in the ocean, and that tunnel will be crossing several faults that could have displacement during a seismic event. And we already mentioned the California high-speed rail that will cross an extension of the Calaveras Hayward Fault here near San Francisco, and it will cross several active faults when going into LA. So those sections will have to be designed to be able to survive after the event, or that the service can be reestablished within a reasonable time. A particular case that I didn't include here is the Anderson Dam outlet tunnel that will be subject to potential displacement of strands of the Coyote Fault during the design event for the dam. So that outlet will have to be operable after the event, so they can release water and lower the reservoir, and it's been designed to survive that event. What are the usual methods to design a tunnel, a concrete lining in the tunnel, and survive the displacement, the fault displacement? Well, articulated lining, as I mentioned for the Bolu tunnel, is one of the strategies that has been used and is being used in some of these tunnels. The concrete lining will have joints that allow displacement, and that way they try to distribute the impact of the fault displacement into several segments. Or another strategy is to enlarge the section where the fault is crossing and allow the fault to displace and still have enough space left in the tunnel to carry the functions that the tunnel is performing. It seems that this is the strategy that has been selected for the Hayward tunnel, for the bar tunnel crossing the Hayward fault. The section will be enlarged. In that case, that's a very good strategy because most of the movement in that particular section of the fault is by creep. So it's a continuous movement, and if they provide an enlarged section, they don't have to do maintenance that frequent. A similar case was selected for the Claremont tunnel, as mentioned before, but they added a steel pipe inside the tunnel. So if the fault moves and there is a collapse, there is that steel pipe will allow water to cross the collapsed section, and it will be easy to reestablish water service to the community after this event. So as we can see, most of the focus of surviving or the seismic event has focused on the concrete lining. But I think we need to go beyond that, and there are already some efforts on trying to look at what happens to the primary support. Right now is only designed for gravity. When we look at, for example, at the Q system, is all based on many case history, so all static loads. It does have some, say, additional strength that is not mobilized just by the gravity laws, but really not known how much. So there have been a couple of studies of trying to figure out if they can extend this method to cover the impact of a seismic event. But definitely this is an area where we need to do more research and at least know where we stand when we design a ground support, be by Q or be by sequential excavation method, NITM, how much additional capacity we have for the case to take care of the additional stresses due to the ground motion. When we look at the design of the concrete lining, again, they are designed following the standard ACI methods, and but we are reaching beyond that. It will be very costly to design many of these tunnels, especially those that are crossing faults, to withstand the movements that can be from a few inches to, if we look at the San Andreas reservoir outlet, 7 or 8 feet. It's not easy to even if you go with the articulated segments, it's not easy to design a structure to take those kind of deformations and still operate. The better you can do is, or the best you can do is try to ensure that it doesn't collapse. And there are many factors that still need to be studied, so we have a better understanding, a better confidence on that what we are doing is going to work. There is some work going on there. We have to consider, for example, that when we are crossing a fault, that the width of the fault is being mobilized during the ground during the earthquake has a big impact. The characteristics of the rock, not only in the fault zone, but the rock adjacent to the fault zone has a big impact on how the ground support and the lining react when the fault displaces. You can see those photographs that I included in the bottom. There are some efforts going on modeling this. So they have a reduced scale tunnel, and they simulate the ground outside. For in this case, it was for fault crossing. So they had a hard rock in one side, hard rock in the other one, and a softer material in between. And this force a displacement of that section, and have been studying what happened to it and the different factors, the strength or the stiffness of the rock in both sides of the fault, the stiffness of the fault gauge, the width, how many segments are included. So there is a lot of research that has to take place, and so we are confident that we know how to design the ground support, not only to take care of the gravity loss, but that we know how much additional we have to support any earthquake loss that will be imposed in the future. Maybe we have to design depending on the location, we have to design the ground support to be able to take an operating basis earthquake loading and leave the safety earthquake loading to the secondary lining, something like that. We still need to come to terms of with criteria for these events. And in the case of fault crossings, it's even more extreme. Right now is basically each entity, say the San Francisco PUC that has tunnels that are going through that, or the East Bay Municipal Utility District that has a tunnel crossing a fault. Right now, in LA Metro is considering the same for, in this case, it's not a tunneling rock, but it will be crossing a fault. The outfall that I mentioned is crossing a couple of faults, and for that particular project, they have defined the design criteria, acceptability criteria of what can happen and how they can take it or not, or accept it or not. But I think as an industry, we need to investigate what happened in the rock during the event, during the seismic event. even in cases where the tunnels survive supposedly without a fracture or anything, we should really know what is happening to the rock. We know in several cases that I have been involved, the tunnels themselves didn't, we went in and there were not new fractures in the tunnel lining, but we did notice that there was more water coming out of the existing fracture because the seismic waves open and close joints in the rock, and once they open, they might not close exactly the same. So the conductivity of this rock mass will change, and it will be directed in different locations, to different locations. So we ended up with the rock with water seeping out in locations that were not there before, and we need to have a better understanding of what happens during an earthquake, and how to mitigate those effects during design, or be ready to do that during the operation. But we need to tell the client that that might happen in the future. Well, I think I got to the time selected for this. So thank you for paying attention to my presentation. And hopefully you have some questions that we can discuss and get to an answer as a group.
All right, thanks, Carlos, for the excellent talk on this very important topic. We have the time now allocated for questions and answers. Please feel free to use the chat option to post your questions, or also use the reactions to raise your hand so we can give you the floor for hearing your question. We can start with the question that's already posted, or those that are already posted. So first question is as follows: is the concrete liner thicker or has more reinforcement in the enlarged sections as shown in one of the slides?
Could you repeat?
Sure. Is the concrete liner thicker or has more reinforcement in the enlarged section?
Oh, well, I guess it will depend on each case. It's a larger section, of course, so even the static loads will be larger. So just from that point of view, the cross section, the thickness of the concrete will be is probably higher, and the reinforcement will be more. But you will have to design it case by case. It cannot be just a general question, answer to that.
Okay, thanks. The second question, what about the water ingress in the tunnel affected by earthquake or by activating a hidden fault zone?
Well, in the case I mentioned at the end, we just have to modify our drainage system to take care of this new location for the leakage into the tunnel. It was a road tunnel, and it was not expected to have water there, so we added panning and take the water so to the side of the tunnel and to the drainage that was already existing there.
I think there was a follow-up to this question, which you kind of pointed out, but let me read it here. Did you see any case regarding the water ingress?
Well, yes, in one of the cases that I mentioned in I think it was the Longship tunnel, several of the new fractures had water coming out. So yes, it has to be taken care of, and it's a common case that after the earthquake, areas that didn't have water produce water in the tunnel.
All right. Thanks, Carlos. So while we wait for the next question, I do have one that I was hoping to ask you. For one of the practices where you showed the enlarged section, what type of material do we end up usually using between the area that is extended or over excavated and the final lining system? So how is that enlarged area filled out?
Yes, it depends. In some cases, they just put the pipeline to extend from one end to the other of the enlarged area, and they are expecting that the ground will collapse on top, but the steel pipe will still allow flow through. We have done some cases where we fill the enlarged section with cellular concrete. So we know that if there is movement, this material will crush and deform, but will still maintain some sort of infill within that area. I have seen cases where they basically fill it with styrofoam, and that way they created well, they didn't leave a void. It was just a different stiffness material.
Okay, thanks. So I think Mohsen has a question. Go ahead, Mohsen, please. I think you're muted still, Mohsen, if you can hear us.
Okay, can you hear me now?
Yes, we can.
Okay, well, I have a experience several years ago, actually about 15 years ago, with the actually heavy shaft in Iran. The project was the Siyavish project, which was steel lined basically, about 400-meter drop. And we were actually crossing a fault, very active fault. And what we did back then was we excavated a much larger section at the location of where the fault was, and passed the steel liner through that and left the remaining portion, surrounding the steel, all hollow by several meters actually, because we were expecting a lot of movement. So I thought maybe I should share that. That was years ago. Again, it was a steel line, it was not concrete. But nevertheless, what we did, we left a big hollow annulus around the pipe itself. So.
Well, thank you for that case history. Yes, that's a well-known project, and it's interesting to know that that was your solution. Did you consider leaving that space open? How the corrosion of the steel lining would have been affected? Because that's one of the reasons why I mentioned, to responding to Reza's question, that we prefer to backfill it with a low density cellular concrete, because it maintains one of the advantages that it maintains an alkaline environment, so the corrosion of the steel is kind of mitigated.
In that particular case, basically we have a cavern around the pipe. I should call it cavern because it was such a huge hollow space. But I don't remember specifically what did we do for the external surface of the steel, whether we painted it or I don't remember. I cannot, remember what did we do as far as the corrosion is concerned. But again, that was the solution. We left it open. Since then, we haven't had any earthquake incident of significance, but because nothing has happened so far. But that was an experience I thought I should share.
Yes, thank you.
Thank you for sharing, Mohsen. So I'm going through the list. We have several questions that hopefully we'll get a chance to cover. Jamal is asking about the stiffness of the lining to deal with the earthquake. Would it be better to have a stiffer or more flexible lining?
In the fault crossing areas?
Yes.
I can imagine, yes.
Well, that's a good question. I guess it has been approached different way by different designers. In one case that we are working on now, we have very stiff cross sections for the segments, and the idea is trying to get all the forces taken by this lining, even if it's going to, we know that it's going to be pushed beyond its capacity, but it will still remain standing, let's say, and protect the pipeline that will be in the middle. In another solution that we have for a different project, for let's say rehabilitation of the San Andreas Reservoir outlet, we place inside a pipe that is very flexible and is surrounded by a low density material. So in that case, the idea is that if there is a movement of the fault in that area, it will, the ground will displace and it will crush the pipe, but there will still be sufficient cross section to allow water to pass through. But it will be deformed by the movement, and so we have used both very stiff and relatively plastic solutions, let's say.
All right, thank you. So next question that I have here is from Hussein, who asked, what is your recommendation for modulus reduction and damping curve for rocks?
I think it depends. You have to look at case by case, and that's one of the areas where we still need a lot to learn of what is the right modulus to use under stiffness to use for the rock mass after we excavate our tunnel. How far to extend that reduce stiffness and modulus of deformation into the rock mass. We know that if we are going with a TBM, that section will be less. If we are going to with drill and blast, we'll create a wider area of affected rock mass, and that will be when we design, we'll have to assume a reduced modulus for that and different stiffness. But I don't think you can have, or there is agreement of how much to reduce those parameters when you are modeling, and you will get different modelers will come up with different assumptions for that.
Thank you.
It also depends on the type of rock that you are excavating your tunnel through.
All right. So there is another question which I think you kind of touched base to some extent, but let me read the question. In some projects, shotcrete is used as final lining. Do you think this can be more effective compared to concrete?
Well, my personal opinion is that shotcrete is just another form of placing concrete. So you will design your lining to be able to carry certain forces. Then you will place it as a reinforced concrete or as shotcrete. Is not just shotcrete is just a different way of placing your concrete, in my opinion.
All right, thanks, Carlos, for that. So this next question we have: near fault zone with high potential of seismic activity, how do you take into in situ stress consideration? Or sorry, in situ stress conditions?
Yes, well, again, if we have a normal fault environment, or we have a reverse fault environment, or those are completely different cases. Your stresses will be completely different. And if it's a slip strike, again, the stress considerations will be different. They will have to take into consideration the seismic environment you are working in. It could be in a thrust fault, your stresses will, in one particular direction, will be higher, and you will have to consider that.
All right. Thanks, Carlos. There was a question related to San Francisco seismic design criteria for tunnels. Are you aware of any public document that might be available online on the seismic design criteria?
I'm sure that the PUC design criteria were published and were public. If you don't find them directly, you can always ask the PUC to release them, because all those documents are available to the public. They might not be in their site directly, but they can be requested.
All right, thanks, Carlos. And unfortunately, we are coming up with the allocated time. So maybe the last question that we can ask, is it better to go deeper to reduce the earthquake damage?
Well, in theory, and some measurements support the idea that the ground motions are less with depth, but you are changing one problem with another one. You go deeper, your stresses will be higher. So I think it's not a solution for this particular case. I think it's better to design your tunnel for whatever requirements you have for operation, and support the ground and reinforce your lining as required for the future loss created by the earthquake.
All right. Thanks, Carlos, for this, and apologies that we couldn't go through the really long but interesting list of questions. Certainly a topic of interest for the rock mechanics tunneling community. So along the same lines, while thanking Carlos for this amazing talk, we are excited to also share our plan for the next webinar, which will be on March 2nd, and offered by Dr. Antonio Bobet of Purdue University along the same lines. So we are excited to have you joining us in our next webinar, again on March 2nd, which would be, I think, a Wednesday, the same time. So please stay tuned for the information on that. And with that, we can conclude this session. Thanks, everyone, and have a great day.
Thank you.
Thanks.